Hi, and welcome to our third video on hydrostatics. And we already went through the hydrostatic equation, and also we derived the hypsometric equation. We discussed the hypsometric equation's uses. We're going to continue on and look at its applications. So we already mentioned that the hypsometric equation tells us why pressure surfaces are higher in some locations above sea level, and in other locations it's lower. We talked about the temperature and how that affects the height of a pressure surface. So the hypsometric equation, if we use one of the limits or define one of the limits z1 as 0, that gives us the height of a pressure surface above sea level. Instead of picking sea level, why don't we look at two different pressure surfaces in the atmosphere? And they could be any pressure surfaces in the atmosphere. One that's commonly used is 1,000 millibars to 500 millibars. So when we pick two pressure surfaces like that, we can look at the distance between those two pressure surfaces. And the distance between those two pressure surfaces is known as thickness. And we represent that with the symbol delta Z. So the problem with calculating thickness is that you have to look at the temperature in a layer. And the temperature, of course, is not constant. The temperature varies. And it depends upon the pressure interval that you pick, the layer that you're looking at. So we have to come up with a way of solving that. So it's kind of confusing. It looks like you can see that temperature doesn't always decrease with height. Sometimes it increases, sometimes it decreases. So the only way to solve this integral is either using a piecewise numerical technique, which you will learn later on in numerical methods in meteorology, or you can estimate or fudge. So that's what we're going to do in this class. We're not going to do any numerical techniques. Instead, we're just going to estimate. And this is actually what meteorologists have been doing for a long time, looking at the average temperature in a layer, kind of estimating using a skew-T log P diagram. They try and get in a layer, trying to put equal areas. In other words, have a point, a line going through point that separates the warm areas and the cold areas of the sounding. So using that average temperature estimated that way, we can put that into the equation. That means that temperature in effect is constant with altitude. Since we picked one altitude, that's the average temperature, one temperature. We'll pull that out, and then we can integrate this integral with defined limits. And you've seen this before, dp over p. Simply integrating that gives you the log, if you integrate it between those two limits, the log of p1 divided by p2. So this is your hypsometric equation, assuming we have an average temperature. If you want to actually calculate the thickness using the variable temperature, you'll have to use a numerical technique. You won't be doing that on the next exam. You'll just be plugging and chugging, so we'll assume average temperatures. And this shows, of course, that pressure decreases logarithmically. You probably knew that already. And you can see that on the sounding also, just by the distance between the pressure isobars, going up vertically through the atmosphere. And it tells you that also the thickness, delta Z, is a function of the temperature. So it depends upon the two layers that you pick, or the two pressure levels that define the layer, and it also depends upon the temperature. And where the air is colder, of course, the thickness is a lot smaller, or it's closer, the two pressure surfaces are closer together. Where it's warmer, the pressure surfaces are farther apart. And of course, this accounts for the slope of pressure surfaces from the equator to the North Pole. And at the North Pole, you see that semi-permanent low low in height, which we commonly refer to as the polar vortex. The polar vortex got a lot of bad press. People think it's something that's new. Polar vortex has been there forever. It just tends to wobble, and sometimes when it wobbles over us, we get cold weather. As I mentioned before, common thickness layer is 1,000 to 500 millibars. If you do the math, you can stick in values, the constants, such as the dry air gas constant, 287, and gravity, or actually G naught, is 9.8 meters per second. And that gives you 20.3 meters times the virtual temperature will give you the thickness of that layer. And of course, thickness is plotted on our surface charts. It's analyzed, and it's one thing that meteorologists use quite frequently to determine temperature and also precipitation type. I hope you enjoyed this discussion on the hypsometric equation.